Module 1, Lecture B, Environment Setup. By the end of this lecture, you will be able to install TensorFlow 2.20 and verify the installation on local or cloud hardware. Configure GPU or TPU acceleration for TensorFlow 2.20 where available. And set up a reproducible project structure for TensorFlow experiments used in this course. TensorFlow Installation Essentials. TensorFlow Install Commands. When installing TensorFlow for this course, use your package manager to install a specific stable version, such as version 2.20.0, rather than the latest release. This keeps everyone on the same setup and reduces compatibility issues. Always do the installation inside a dedicated environment, like a virtual environment or a Conda environment, so it does not interfere with other projects. On Windows, macOS, or Linux, activate your environment, run the install command, and let the package manager automatically download and configure everything needed for your system. Installing TensorFlow on a cloud platform works much like installing it on your own machine, except you may run the commands in a notebook cell instead of a terminal. Cloud environments often come with TensorFlow pre-installed, but it might not match the version required for your course. In that case, you install the specific version, such as 2.20, to replace or adjust the existing one. You should treat this installation step as the first thing you do in any new environment, whether it is a laptop, a lab computer, or a cloud notebook, before starting your work. Installing TensorFlow can take some time because it has many dependencies, so you should let the process finish without interruption and watch for any warnings or errors. Problems like an unstable internet connection or restricted permissions on a corporate laptop can cause the installation to fail, and you may need to reconnect or use a user-level environment to fix them. As you gain experience, you will get better at recognizing the difference between normal installation messages and real errors, which will make setting up environments for new projects easier. Handling CUDA and cuDNN versions. To use GPU acceleration with TensorFlow, you need compatible versions of TensorFlow, CUDA, and cuDNN. CUDA is NVIDIA's GPU computing platform, and cuDNN is a library that speeds up deep learning operations. TensorFlow's GPU-enabled builds are tied to specific CUDA and cuDNN versions, so version mismatches can cause GPU access errors. Instead of installing the newest CUDA and cuDNN, make sure you install the versions required by your TensorFlow 2.20.0 installation. To manage CUDA and cuDNN for TensorFlow, first check which versions are officially supported by your specific TensorFlow release, and align your system to those. On a local machine with an NVIDIA GPU, make sure your graphics driver supports the required CUDA version. Then install that exact CUDA toolkit along with the matching cuDNN version. In a cloud environment, confirm that the pre-installed CUDA and cuDNN versions match TensorFlow 2.20.0, or select a runtime that explicitly supports it. Following this process keeps your setup compatible with TensorFlow and helps prevent configuration issues. Treat CUDA and cuDNN as core parts of your environment setup, just like your Python and TensorFlow versions. Whenever possible, use pre-built combinations, such as container images that already bundle TensorFlow with compatible CUDA and cuDNN, so you do not have to manage these libraries yourself. Carefully record which versions you use and share this information with your team, so everyone works with the same setup. This strategy reduces version conflicts, simplifies debugging, and provides a stable base for running TensorFlow efficiently on supported GPUs. Confirm TensorFlow version. After installing a library, you should always check which version your environment is actually using. It is easy to assume the new version is active when an older one is still in place, which can lead to confusing errors. Verifying the version right away gives you a clear baseline and confirms you are working with the intended software. This simple step is important whether you are on your own laptop, a shared university machine, or a cloud notebook. Checking the version of a library ensures that your environment is actually using the one you expect. On a local machine with virtual environments, you want to confirm it matches what you installed, not an older system-wide version. In cloud or hosted notebook setups, you should verify whether the code is using a pre-installed library or the one you added. This becomes especially important when switching between projects, since each may require a specific version, and using the wrong one can cause subtle, hard-to-debug errors. Regularly checking software versions is important, especially when starting a new session or returning to a project. System updates or changes made by colleagues can leave you running different versions, which may affect performance and features. By confirming versions before key experiments, you keep your work reproducible and make it easier to share and compare results. This consistency also simplifies debugging and supports smoother collaboration with others. Python code. Confirm TensorFlow version. This script is used to check which version of TensorFlow is installed in your environment. You should run it after you finish installing TensorFlow. By confirming the version, you can make sure that the correct release required for this course is available and ready to use. If TensorFlow is not already installed, there is a commented instruction showing how to install it with the pip package manager. This instruction specifies installing TensorFlow version 2.20.0. By uncommenting and running that command, you ensure the correct version is installed and compatible with the course requirements. This code imports Python's system module, which gives access to system-specific information and functions. In this script, it is used to check the current Python version. This helps verify that the Python environment is compatible with the installed TensorFlow package. The code tries to import TensorFlow under the usual alias, and if that fails, it catches the import error. It then reports that TensorFlow is not available in the current environment and recommends installing version 2.20.0. After displaying this message, the script stops running and exits with an error status using the original import error as the reason. We first check the current Python version by reading the system version information from the sys module. Then, we split this version string to extract the main version number, usually the first part. Knowing this main version helps us confirm that it is compatible with the installed TensorFlow version and with any other tools that depend on a specific Python version. We obtain the currently installed TensorFlow version by reading its version attribute through a safe getAttribute call. If this attribute is missing, we fall back to the value unknown. This simple check tells us exactly which TensorFlow version is active, which is important for later compatibility checks in the script. In this course, we set the required TensorFlow version to 2.20.0. This version acts as a standard for what should be installed so that all course materials and examples work correctly. By specifying it clearly, we can later check whether the installed TensorFlow matches this requirement. This helps maintain consistency across environments and prevents problems caused by version mismatches. This script first reports the version of Python that is currently running to confirm the environment is set up correctly. It then reports the installed TensorFlow version. Checking both versions is important to ensure they match the requirements of the course and that everything is compatible before you continue. This code checks whether the installed TensorFlow version matches the version required for the course. It compares the current TensorFlow version string to the expected one, and, if they match, confirms that the setup is correct. If they do not match, it issues a warning and reports both the required version and the version that is actually installed. This helps ensure the environment is properly configured for the course material. We create a small constant tensor using TensorFlow as a simple test to confirm that the library is working correctly. If this basic operation fails, it signals a problem with the TensorFlow installation or configuration. In that case, we catch the exception, report that TensorFlow was imported but its basic operations did not work, and then exit the program with an error. This step ensures TensorFlow can perform fundamental tasks before we proceed with more complex operations. The script first checks the shape of the tensor created earlier by converting it to a tuple and comparing it to the expected 2 by 2 dimensions. If the actual shape does not match this expected shape, it signals a possible misconfiguration. In that case, the program prints a warning message to inform the user. It then exits with an error status to stop further execution until the issue is fixed. This line prints a confirmation message showing that TensorFlow has successfully run a simple tensor operation. It serves as a final check that the library is installed and working properly in the current environment. By seeing this message without any errors, you know that basic TensorFlow operations can be executed correctly. This script verifies your TensorFlow setup by first checking that TensorFlow is installed and prompting you to install version 2.20 if it is missing. It then reports the current Python and TensorFlow versions and compares them to the expected TensorFlow version 2.20, warning you if they do not match. Finally, it creates a small constant tensor and runs a simple operation to confirm that TensorFlow executes correctly, indicating that your environment is properly configured. TensorFlow hardware acceleration. Detecting available devices. When using hardware acceleration with TensorFlow, the first step is to check which devices it can actually access on your system. Even if you have a GPU or a TPU available, TensorFlow needs the correct drivers and libraries before it can use them. Detecting these devices serves as a diagnostic step to see whether TensorFlow recognizes only the CPU or also GPUs and TPUs. This verification is important because it determines the performance you can expect and can be the difference between training a model in minutes or in hours. To detect available devices in TensorFlow, you ask it to list both logical and physical devices, then interpret the results based on your needs. On a typical laptop, this usually shows a CPU and, if configured correctly, a GPU, while more powerful systems may list multiple GPUs for parallel training. In cloud environments, the devices can change depending on the selected runtime, such as switching from CPU to GPU. Regularly checking this device information helps you quickly spot problems like missing GPU drivers or misconfigured environments. Device detection in TensorFlow helps you choose how to run your workloads and diagnose performance problems. If you only see a CPU when you expect a GPU, it may indicate system issues such as driver or library problems. When multiple GPUs are visible, you can plan how to distribute training, keeping in mind that each GPU may have different memory and compute capacity. In shared environments like research clusters, device detection can reveal administrator limits on GPU access. Regularly checking which devices are available, especially with cloud TPUs, helps confirm that everything is configured correctly before starting expensive training runs. Python code, detecting available devices. This lesson introduces the basics of detecting devices in TensorFlow. You will see how to list the hardware that TensorFlow can use. This helps you confirm whether your CPU, GPU, or TPU is visible and available for computation. The commented line with the exclamation mark is a command to install TensorFlow version 2.20.0. This specifies an exact TensorFlow version to keep the script compatible with the rest of the code. The exclamation mark shows it is meant to be run as a shell command in a Jupyter Notebook or similar environment. Because the line is commented out, it indicates that installing TensorFlow is optional or has likely already been done, and the script expects TensorFlow to be present in the environment. The code starts by importing the operating system module, which lets the script interact with the computer's operating system. This module is used to access environment variables and perform system-level tasks. In this context, it helps prepare the environment so the script can carry out later operations, such as checking what hardware devices are available. This code tries to import TensorFlow, a common library for machine learning. If TensorFlow is not installed, it catches the resulting import error and informs the user that TensorFlow is unavailable in the current environment. It then suggests installing version 2.20.0. Finally, the program exits with an error status code of 1 to indicate that it cannot continue without TensorFlow. This line displays the version of TensorFlow that is currently in use. It provides a quick way to confirm that the correct version is installed and running in your environment. Checking the version helps ensure your code is compatible with the library. It also lets you verify that any needed features or bug fixes from a specific TensorFlow release are available. This function prints a brief summary of a set of devices. It takes a label and a list of devices, then shows the label along with how many devices are in the list. After that, it goes through each device and prints its name and type. This provides a quick overview of what devices are available and what kind they are. We start by using TensorFlow's configuration tools to list the logical devices available for computation, such as CPUs and GPUs. This list is stored for later use. We then call a helper function that takes a label describing the list and the list itself, and prints a summary of each device. The printed summary includes the device names and types, allowing us to confirm which hardware resources TensorFlow can use to run operations. We begin by asking TensorFlow to report all the physical devices it detects on the machine, such as available hardware for computation. The list of detected devices is stored for later use. Then we call a helper function that takes a label and this list and prints a brief summary. It reports how many devices there are and key details about each one, including its name and type. This gives us a quick overview of the hardware resources TensorFlow can use. We use TensorFlow's configuration tools to get a list of all physical devices that are GPUs, so we can see whether any GPU resources are available. Then, we pass this list to a helper function that prints a short summary, including the labeled GPU devices, the number of GPUs found, and each device's name and type. This quick check confirms that TensorFlow can access the GPU hardware, which is important for speeding up deep learning computations. To check whether tensor processing units are available, we use a TensorFlow configuration method that lists all physical devices of type TPU. This call returns any TPU devices that TensorFlow can access. We then pass this list to a helper function that prints a brief summary of each device, including its name and type. Together, these steps confirm whether TPU resources are present and ready to use for acceleration. This code checks which hardware TensorFlow can use for acceleration. It first looks for any available GPU devices, and if it finds at least one, reports that a GPU is available. If no GPU is detected, it then checks for a TPU and reports if one is present. If neither a GPU nor a TPU is found, it reports that only the CPU is available. This logic helps identify the best hardware option for running TensorFlow operations efficiently. This script uses TensorFlow to check what computing devices are available on your system. It first confirms that TensorFlow is installed and reports its version. Then it lists the logical devices that TensorFlow can use and the physical devices that represent the actual hardware. The script looks specifically for GPUs and TPUs and reports whether they are present or if only CPUs are available. This lets you quickly verify whether your environment can use hardware acceleration for TensorFlow operations. Managing GPU memory. When you use hardware acceleration with TensorFlow, it is important to control how GPU memory is used, because this memory is limited and shared by all running processes. If your model needs more GPU memory than is available, you can get out-of-memory errors, especially with large batches, big input images, or very deep networks. Understanding how TensorFlow interacts with GPU memory helps you adjust your model and training settings to fit your hardware limits, avoid crashes during long runs, and share resources fairly on shared servers or cloud machines. TensorFlow includes options to control how it uses GPU memory, which is important on shared or limited machines. By default, it may reserve most of the GPU to speed up training, but this can cause problems when other applications also need the GPU. A better approach is to let TensorFlow grow its memory usage gradually during model execution so multiple tasks can share the same GPU. This makes it easier to run tools like notebooks or dashboards alongside training and allows several users in a shared environment to run experiments at the same time without interfering with each other. When working with GPU memory, focus on how your model design affects usage, especially batch size, input resolution, sequence length, and model depth. On limited hardware, such as a laptop GPU, you may need to reduce batch size or simplify the model, which can slow training but improve stability. For demanding tasks like high-resolution imaging or long language sequences, cropping or downsampling can help keep memory under control. Regularly monitoring memory with system tools and understanding these design trade-offs lets you plan experiments more efficiently without constant trial and error. Python code, managing GPU memory. This script introduces basic ideas about GPU memory in a simple way. It relies only on standard Python and prints short summaries of what is happening. The goal is to help you understand the core concepts before moving on to more complex tools. You can later adapt these ideas when you start working with real TensorFlow code. This script runs using only standard Python and does not depend on any external libraries. If you are working in Google Colab, you would need to install TensorFlow separately for it to run there. A sample install command for TensorFlow version 2.20 is included but commented out. This is done on purpose, so the script stays simple and focuses on explaining the concepts rather than actually running TensorFlow. The script starts by importing the operating system library so it can work with the system's environment variables. These variables control configurations and settings that influence how the program runs, including access to hardware resources like GPUs. By using this library, the script can check and adjust these variables as needed, helping the program run correctly and consistently across different environments. We define a helper function that turns a raw byte count into a more readable size. It uses a list of units from bytes up to gigabytes and converts the input to a floating point number for accuracy. The function repeatedly divides the size by 1024 and moves to the next unit as long as the value is large enough and higher units are available. In the end, it returns the size rounded to 2 decimal places along with the chosen unit, making large byte values easier to understand at a glance. We simulate a total GPU memory of 4 gigabytes to create a realistic environment for teaching. This amount is converted into bytes, so it matches how memory is handled in actual systems. Using this simulated value lets us explore GPU memory management concepts in a controlled setting without needing real GPU hardware. This description explains a simple model of how TensorFlow might reserve GPU memory in a greedy way. Given the total GPU memory and a reserve ratio, it first computes how much memory to reserve by multiplying these two values. It then finds the remaining free memory by subtracting the reserved amount from the total. The result is a pair of values showing how much memory is reserved and how much is left for other processes when a large portion is taken up front. This description explains a function that models how GPU memory usage increases over time. It begins with no memory used and repeatedly adds a small amount based on a fraction of the total available memory. At each step, it makes sure the used memory never exceeds the total capacity and records the current usage. In the end, it returns a list of these recorded values, showing how memory usage grows step by step. The script starts by printing a header message to the console that explains its purpose. It tells the user that the program will conceptually simulate how GPU memory management works. This is only a simplified, illustrative model and does not perform any real GPU operations. The message sets expectations so the user understands that what follows is a teaching tool, not an actual GPU management system. This example demonstrates how greedy allocation of GPU memory works in TensorFlow. A function simulates TensorFlow reserving a large portion of the total GPU memory, such as 90%, and returns both the reserved amount and the remaining free memory. We then display a message that explains this behavior and use a helper to convert the raw byte values into a more readable form. This makes it clear how much GPU memory TensorFlow might claim upfront and how much is left available for other processes. We simulate how GPU memory usage can gradually increase over several training steps by calling a function that models incremental growth. This function takes the total available GPU memory, a step size of 15%, and the number of steps, then returns the memory usage for each step. We then announce that we are simulating TensorFlow's gradual memory usage and loop through the returned values. For each step, we print the step number and the corresponding memory usage in a human-readable format. This simple process illustrates how memory consumption can rise over time during training. The code defines a few example batch sizes, such as 8, 16, and 32, to show how changing this setting affects GPU memory usage. Using these specific sizes, the script can estimate how much memory each one would require during training. This helps you see the relationship between batch size and memory consumption in a concrete way. We set a constant value of 64 megabytes to represent the memory required for each sample in our simulation. This fixed amount lets us estimate how much GPU memory is needed for different batch sizes. By multiplying this per sample memory by the number of samples processed at once, we can see how total memory usage scales with batch size. We examine how different batch sizes affect GPU memory usage by going through a list of example batch sizes and estimating the memory each one needs. For every batch size, we multiply it by a constant that represents the memory required for a single sample to get the total memory for that batch. We then convert this value into a human-friendly format with a helper function and print a message showing the memory needed. This process makes it clear how increasing or decreasing the batch size changes overall GPU memory consumption. This script is a simplified simulation of GPU memory management that does not rely on actual hardware or TensorFlow. It first models a case where TensorFlow reserves about 90% of the GPU memory at once, leaving only a small amount for other tasks. It then shows memory usage gradually increasing in several steps, with each step consuming an additional portion of the total memory. Finally, it illustrates how memory use grows with batch size, when each sample requires a fixed amount of memory. Together, these simulations help you understand how GPU memory might be allocated and used in real machine learning workloads, and how this affects memory management strategies. Colab and cloud TPUs. In hosted environments like Google Colab, you can access powerful GPUs or TPUs without owning the hardware. But you must understand how they are configured. You select a runtime with an accelerator, and the system launches a virtual machine that includes that device. It is important to confirm that TensorFlow version 2.20 detects and uses the accelerator by checking both the runtime settings and the TensorFlow version, and by verifying that the device is active when your model runs. Because Colab sessions are temporary and can change each time you reconnect, always treat it as a short-lived workstation and recheck your environment whenever you start a new session. Cloud TPUs are more complex to use than local GPUs because they act as remote accelerators that your TensorFlow program reaches over the network. You request a TPU runtime, receive an address, and TensorFlow connects and distributes work across the TPU cores, but only for operations that the TPU supports. Because data transfer over the network can become a bottleneck, it is important to keep data close to the TPU, for example in a nearby cloud storage bucket, and to design efficient input pipelines so that TPU cores stay busy. Overall, you should think of the TPU as a remote, high-throughput engine that requires careful attention to data locality and supported operations, rather than something that behaves like a local GPU. When working with Colab and cloud TPUs, you need to manage temporary sessions, quota limits, and reproducibility carefully. Because Colab sessions can disconnect without warning, keep your key setup steps, such as TensorFlow version checks, at the top of your notebook or in a script so you can rerun them quickly. In cloud environments, define your software stack and settings in configuration files so every TPU instance uses the same TensorFlow setup. This consistency makes it easier for teams to collaborate, compare results, and debug performance issues across both Colab prototypes and dedicated TPU experiments. Python code, Colab and cloud TPUs. This script quickly checks whether a Colab runtime has access to a GPU or TPU. It is used to confirm that TensorFlow can use hardware acceleration. Run it after you switch the Colab runtime to either GPU or TPU to verify that the selected accelerator is available and working. The line that begins with an exclamation mark is a command to install TensorFlow version 2.20. It is commonly used in notebook environments such as Google Colab to make sure that this specific version is available. By doing this, the notebook manages its own dependencies and ensures the code runs with the expected TensorFlow features and fixes. We start by importing 3 key libraries. The operating system library lets us interact with the system environment. The random library provides tools to generate random numbers, which can be made reproducible by setting a seed. Finally, we import NumPy, a numerical computing library that efficiently handles arrays and mathematical operations. We set a fixed seed value of 42 for both the standard random module and for NumPy's random number generator, so that any random values they produce are the same every time the code runs. This makes the behavior of the program deterministic, instead of changing from run to run. Such reproducibility is important for experiments, testing, debugging, and verifying results because it removes uncertainty caused by random number generation. The script begins by trying to import TensorFlow, which is required to run its machine learning tasks. If this import fails, it causes an import error, In that case, the code immediately raises a system exit, stopping the program. It also shows a message indicating that TensorFlow is not installed correctly. This approach catches TensorFlow installation problems early and prevents later errors in the script. This line of code displays the version of TensorFlow that is currently in use. It reads the version information stored inside the TensorFlow library and prints it out. This allows you to quickly confirm which TensorFlow version is installed and running in your environment. This code uses a TensorFlow configuration function to list all physical devices of type GPU. It then counts how many GPUs are found and prints that number. This provides a quick way to confirm whether any GPU hardware is available for accelerating computations. We begin by using a TensorFlow configuration method to list the logical devices in the system and check specifically for any TPU devices. This step tells us whether TPU hardware is available to accelerate our computations. We then print how many TPUs were found so we get immediate feedback on their availability before proceeding. The code chooses the best available device for testing by checking hardware in order of power. It first looks for TPU devices and uses the first one if any are found. If no TPUs are available, it then checks for GPUs and uses the first GPU if possible. If neither TPUs nor GPUs are present, it falls back to the CPU. This approach helps the code automatically run on the most powerful hardware available to improve performance. The code prints a message showing which device will run a small test. It first checks if a TPU is available, then looks for a GPU, and if neither is found, it uses the CPU. This confirms the hardware that will execute the next operations and ensures the test runs on the intended device. We start by creating a small fixed tensor using TensorFlow's constant function. This tensor is a 2x2 matrix containing the values 1, 2, 3, and 4. It serves as a simple, predictable input for testing computations on different hardware devices, such as GPUs or TPUs. Because the tensor is constant, its values never change, which makes it easier to verify that later operations in the script are performed correctly. Before doing any work, the code first checks that the tensor has a shape of 2x2. This validation step makes sure the upcoming matrix multiplication can run safely. If the tensor does not have this exact shape, the code raises a value error. This signals that the tensor is not in the correct format for the test matrix operation. This code uses TensorFlow to perform a simple matrix multiplication while explicitly choosing the hardware device, such as a CPU, GPU, or TPU, depending on what is available. By using TensorFlow's device selection feature, it ensures the computation runs on the specified hardware. The operation multiplies a 2x2 constant tensor by itself, serving as a basic test. This confirms that the selected device is correctly set up and working for TensorFlow computations. This code takes the output of a TensorFlow operation and converts it into a NumPy array. Doing this makes the result easier and safer to print. NumPy arrays are designed for handling numerical data efficiently in Python, so they are a convenient format for viewing and working with these results. This code displays the result of a matrix multiplication test. It first prints a short message to indicate that the test result is coming, then shows the computed matrix. The result is converted to a NumPy array, so it is easy to view. This output confirms that the matrix multiplication was successfully carried out on the chosen device, whether that is a GPU, TPU, or CPU. At the end of the script, a message is printed to confirm whether hardware acceleration is working. It reports the type of device being used and explains that if the device is a GPU or a TPU, then hardware acceleration is active. This final message serves as a quick check that the computation is running on the intended hardware resources. This script uses TensorFlow in a Colab environment to check whether GPU or TPU hardware acceleration is available and working. It first sets deterministic seeds for reproducibility and confirms that TensorFlow is installed by importing it and printing the version. The script then counts how many GPU and TPU devices are detected and chooses a device to test, preferring a TPU, then a GPU, and falling back to the CPU if needed. On the selected device, it runs a simple matrix multiplication with a small 2x2 tensor, converts the result to a NumPy array, and prints it. If this operation succeeds on a GPU or TPU, it confirms that hardware acceleration is functioning correctly. TensorFlow project setup. Project folder structure. When starting a new TensorFlow project, it is important to organize your files and folders in a clear, consistent structure. This makes it easy for you and collaborators to find data, models, and results, and to see which code and settings produced each model. Good organization is especially important for complex tasks like image classification or time series forecasting, where experiments can quickly become hard to track. A well-structured project prevents your work from becoming scattered and reduces the effort of managing files, so you can focus more on analysis and modeling. Organize your TensorFlow project folder to reflect the main stages of your workflow: data handling, model development, training and evaluation, and reporting or deployment. Keep raw data separate from processed data and group scripts and utilities by what they do. Save outputs such as model checkpoints and training logs in clearly labeled folders so you can link them to specific experiments. Including details like dates and short descriptions in experiment outputs helps you track configurations and results, turning your project into a clear record of your work and decisions. Keeping a consistent folder structure in your TensorFlow projects is essential for clarity and collaboration. A standard layout helps you quickly find data, models, and logs, even after time away from a project. It also makes it easier for new team members to navigate your work without needing detailed explanations. In research or industry settings, a shared structure supports smooth movement between projects and enables automated tools for testing and deployment. Treating folder organization as part of your project design improves reproducibility, auditability, and overall workflow efficiency. Virtual environments basics. When working on machine learning projects, it is important to use a virtual environment so your dependencies stay isolated. This lets you install the exact version of TensorFlow and other libraries you need for each project without affecting other work or system-wide packages. As a result, different projects can safely use different TensorFlow versions on the same machine. This separation helps prevent version conflicts and the bugs they can cause. Virtual environments are important for making projects reproducible. By creating a separate environment for each project, you can record the exact packages and versions you used. This keeps your work consistent when you share it or return to it later, even if the system has changed. It also lets you recreate the same setup on different machines, so your code continues to run as it did originally, without unexpected issues from system-wide updates. In TensorFlow projects, using a virtual environment should be a standard part of your workflow. For each new project, create and activate a fresh environment before installing TensorFlow and any related tools, and always run your notebooks and scripts inside it. This is especially important on shared systems such as university labs, where global package installs can cause conflicts, and in industry, where teams need consistent development, testing, and production setups. Making virtual environments a routine step in your project setup leads to cleaner, more organized, and repeatable experiments. Python code, virtual environments basics. This script is meant to help you understand the idea of virtual environments, but it does not actually create or manage real ones. Instead, you use it as a conceptual tool to picture how each project can have its own isolated set of dependencies. Think of it as a way to visualize separation between projects, not as a tool for performing real environment operations. We define a class called virtualenv to represent a virtual environment, and we initialize it with a name stored in an instance variable. The class also creates an empty dictionary to track package names and their versions. This design lets each virtual environment keep its own set of dependencies separate from others, so different projects can manage their packages independently. The install method is used to add or update a package in a virtual environment by taking the package name and its version as inputs. It stores the given version for that package in the environment's packages dictionary. This updates the record of which version is installed in that specific environment. As a result, each virtual environment can keep its own independent set of package versions and dependencies. This method builds a text description of an environment by first creating a header line that includes the environment name. It then goes through the dictionary of packages and versions in alphabetical order. For each package, it adds a line showing the package name and its version. Finally, it joins all these lines with new line characters into one formatted string that represents the environment's configuration and returns that string. We create two separate virtual environments to manage dependencies independently. One environment, named for the course, is used to install packages needed in a teaching setting. The other environment, named for research, holds a different set of packages and versions suited to research work. Keeping these environments separate prevents their configurations from interfering with each other. In this part of the code, we install specific package versions into the course environment, including TensorFlow version 2.20.0 and NumPy version 1.26.0. Using exact versions ensures compatibility with the course materials and with any dependencies these libraries rely on. This setup shows how a virtual environment can keep its own isolated set of package versions, providing a consistent and reproducible setup for the project. In this part of the script, we set up the research environment by installing TensorFlow version 2.22 and NumPy version 2.0. Using specific versions ensures the research environment has exactly the tools it needs, regardless of what is installed elsewhere. This approach lets the research environment keep its own set of dependencies, which can differ from those in the course environment. Overall, it demonstrates how virtual environments provide isolation and flexibility by allowing each environment to use its own tailored package versions. To show that each virtual environment keeps its own package versions, we first announce that we are listing the packages for the course environment. We then use a describe method on the course environment object, which creates a formatted summary of the environment's name and all installed packages with their versions. The resulting output makes it clear that this environment has its own isolated set of dependencies, separate from other environments. The code prints a blank line to visually separate the outputs from two different virtual environments. This separation makes it easier to see where one environment's package configuration ends and the next one begins. As a result, the displayed results are clearer and less likely to be confused with each other. We start by printing a short message to signal that the package configuration for the research environment is about to be shown. Then we call a describe method on the research environment object, which gathers the installed packages and their versions and formats this information into a readable summary. Finally, we print this summary so we can see exactly which package versions are installed, emphasizing that this environment is isolated and independent from other setups. This script uses a simple virtualenv class to simulate how Python virtual environments keep package versions separate. It creates two environments, one for a course and one for research, and assigns each its own versions of TensorFlow and NumPy. The course environment uses TensorFlow version 2.20 and NumPy version 1.26, while the research environment uses TensorFlow version 2.22 and NumPy version 2.0. By printing the package setups for both, the script shows that each environment can maintain different versions of the same libraries, illustrating isolation and dependency management without actually creating real virtual environments on your system. Git workflow for TensorFlow. When running TensorFlow experiments, a disciplined Git workflow is essential for keeping your work organized and reproducible. Git acts like a time machine for your code, recording each stable point, such as new pre-processing steps or model architectures. By making clear commits whenever you change things like learning rates or optimizers, you build a history that shows exactly when and how your models evolved. This is especially important in TensorFlow, where small adjustments can greatly affect performance, and you often need to revisit or reproduce earlier versions for reliable experimentation and reporting. In a TensorFlow project, using Git branches lets you keep a stable main version separate from experimental work. You keep reliable code on the main branch and create feature branches for new ideas, such as architecture changes or data augmentation. Clear commit messages help you track each experiment and avoid mixing them together. When an experiment works well, you can merge that branch back into the main one. This approach also supports teamwork by making it easier to review, discuss, and safely integrate changes. For reproducible TensorFlow projects, use Git to track all files that control how experiments run, such as model configurations and scripts for data processing and training. Do not store large artifacts like datasets or model checkpoints in version control. Instead, clearly document where they are kept and how to recreate them. Maintain a brief experiment log in the repository that records major runs, the branches or commits they used, and key results such as accuracy trends. This creates a clear audit trail that makes it easier to revisit, share, or publish your work and to show exactly how to replicate it. In this lecture, you learned to install TensorFlow 2.20 and verify the installation on local or cloud hardware. Configure GPU or TPU acceleration for TensorFlow 2.20 where available. And set up a reproducible project structure for TensorFlow experiments used in this course. In the next lecture, Lecture C, we will go over TF 2.20 overview. Thank you for your attention. See you all in the next lecture.